Hi everyone, so today we'll look at how do we know that Rayo's number is bigger than Loader's number, and why is Loader's number bigger than 33, and how is 33 bigger than Graham's number. So we're gonna look at this today, and I try to explain it in a layman way, although this could be, very hard to understand. And I got asked this question a lot. So let's get started. So first of all, how do we know 33 is bigger than Graham's number? Again, there are some proofs online on the Googleology wiki. There are links to the proof, but the proofs, they are mostly not layman. Pretty hard to understand. So I'm going to try to explain this quickly and briefly. So in order to understand this, well, there are two ways to look at this. First of all, of course, we looked at the growth rate, which is related to the fast growing hierarchy. And some people can show or prove that, of course, it's easy for Graham's number or G sequence. The growth rate is just F, which is the fast growing hierarchy, F of omega plus 1, and this is the growth rate of the Graham sequence. And it can be shown that the tree sequence grows much faster than that. So this is one way we can see how 33 is much bigger than Graham. However, this is not the most proper way to do it, because there are exceptions, such as G1 of Graham's number. G1 is, of course, greater than Cherry 1, and 33 is much bigger than BCB for 3, and also 33 is much bigger than Rayo's 3. So this is not 100% way to see how two numbers, let's say 33 is bigger than Graham's number. Even though 3 grows much faster, it might not grow as fast at the beginning. So another way, more accurate way to see how tree 3 is much bigger than Graham's number is actually you look at the structures of the tree. So let's say you start drawing out all the trees for tree 3. So you start from, the first one, second one, third one, etc. You keep going until you reach tree 3. So of course, K1, this is just, I draw it randomly. It doesn't have to be like this in reality. So it can be shown in some proofs that, let's say you draw the first one, this is the second one, this is the third one. And of course, eventually you can draw, for example, this tree over here. And you can prove that between, let's say, the third tree and this tree over here, KN, let's say KN, in between these two trees, there are at least G64 number of terms. Of course, this number is much bigger than G64. I'm just showing you an example. It can be proved that between, let's say, two branch of trees, you can plug in at least this many trees. And this number is much greater than Graham's number. And this can already prove that tree 3 is much bigger than Graham's number. So n in this case is much bigger than Graham's number. And of course, this is not the end. You can still keep going until you reach tree 3 number of trees. It just show that it can be proven that between, let's say somewhere between two trees, you can plug in more than Graham's number of trees in the middle. Again, proves is online, is not layman, but this is the layman explanation. And then the second thing is, how do we know that Loader's number is bigger than 3? Well, this is a little bit harder because both of these numbers are so big. At least Graham's number, it is how big is Graham's number, so it's a lot easier to show this one. This is more difficult. Some people still don't think Loader is bigger than 3. However, this is again just a layman explanation. So first thing, we look at the codes, because Loader's number is a C program. We look at the codes of the Loader's function. It is actually, in a layman way, is a baby BC Beaver, or a mini BC Beaver. It's a computable version of BC Beaver. I mean, this is just, how we can describe it is similar in some way. And it is used, it used the calculus of construction, COC, which is somehow similar in power, in terms, it's very powerful, almost as powerful as the Turing machines. Again, this is just a simplified version of explaining this. And now we look at what is D99. So D99 is basically we can say that you put together all the COC programs that can be made in 99 steps. So N here stands for, DN is just how many steps in those programs, and you put together all the outputs. And for that reason, D99 is already quite big. So you simulate all the programs that can be made in 99 steps, and the final output you put together is at least 2 to the 2 to the 2 to the 2 for 30,419 levels. So this is already a pretty big number, much bigger than Googleplex, etc. And this is just D99. And what about D of D99? D of D99, of course, you put together all the programs that can be made in D99 number of steps, which is this huge number here. So D99, basically, to simplify it even more, you can say what is the biggest number you can create with all the programs that can be made in 2 to the 2 to the 2 for 30,419 steps. So obviously this is an unbelievable large number. It can be shown to be much bigger than Goodstein. Any number, I mean not any number, it is more powerful than a Goodstein sequence, which is already pretty powerful, and possibly even 3 at this stage. However, there's no 100% guarantee. However, if you put one more D here, so D of D99 or D399, you put together all the COC programs that can be simulated in D of D99 steps. And D of D99 is already an unimaginably big number. And a lot of people believe that this number, D of D399, is already most likely much bigger than 3. And if that's the case, it's probably going to be much bigger than 3, etc. and so on. However, Loader's number is not D399, it's D599 with 5 Ds. So I'm not sure if there's a proof of this, but I think it's safe to say Loader's number in that case is much bigger than 3 or the 3 sequence, because of the way you constructed it. It's a computable function. 3, same as 3, is a computable function. The way you construct it, the Loader's function is very similar to the BC Beaver. And of course, BC Beaver is much more powerful than 3 and is uncomputable. So the way it constructed, 3 doesn't require this many steps, to construct the 3 function. So based on that, we're safe to say Loader is much bigger than 3. And then the last one, how is Rayo's number bigger than Loader? Well, this is not too difficult actually, because Loader's number is computable. All COC programs are computable, and therefore it must grow slower than BC Beaver function. For BBN for small n, say n is 1,000. So BC Beaver 1,000 is much bigger than Loader's number. Actually, there's some proofs online. BC Beaver 1919, so 1919 is already a unprovable number, which in other words is an uncomputable number. That means BC Beaver 1919 is already much greater than Loader's number or 33 or whatever, all the computable numbers. It is uncomputable because it cannot be shown. It cannot be proven in the ZFC theory. You cannot prove BC Beaver 1919 whether it holds or not. So therefore, we don't know. We cannot prove it holds or not. Therefore, it's an uncomputable number. In other words, much greater than any computable number. And in other words, on the other hand, Rayo's function is much more powerful than the BC Beaver, simply because the language of the first order set theory is a lot more powerful, a lot more descriptive and expressive and efficient than the formalism of Turing machines. So at first, it might not grow as fast as the BC Beaver. However, in the long run, let's say maybe 1 million symbols, once you can construct the Turing machine codes in the language of first order theory, which doesn't require too many, once you construct that, then easily it can beat the BC Beaver very easily. Maybe just add a few more symbols, you can already beat the infinite Turing machine, something like that. So And of course it's uncomputable. So since Rayo's number is way more powerful, way more efficient, way more descriptive than the Busy Beaver, and Busy Beaver of course much bigger than Loader, is uncomputable, Loader is computable, so that way we can show Rayo is much bigger than Loader. So there we have it. This is just a quick layman and brief explanation of how this is true. Rail bigger than Loader, bigger than Tree 3 and G64. Again, proofs are on the Googleology Wiki or online. You can click on the links and show it. And again, they are not that layman. So anyway, thanks for watching and have a nice day.